questions. And we'll move on to our next speaker, who is Ron Shamir from the School of Computer Science here at Tel Aviv University.
I'm going to talk about work led by Omer Noy, who is here, and Dan Koster from my group, together with Maya and Itai from Tel Aviv. And this is a collaboration with clinicians, Shani Shenhar, Shlomo Berliner, Onor Rigovsky at Ichilov, and Galia Rahav at Shiba. So we focused on the first three waves of the pandemics. The point where vaccinations got into Israel were at the beginning of the third wave, and therefore we looked at data available for until the vaccination started. And the question that we asked is, of those patients who are hospitalized, who is likely to deteriorate? So the goal is to develop a model to predict those patients who are at risk for deterioration. And of course, the benefits are that if we know this well in advance, we can treat the patient or take care of them more carefully. And also on the world level, if you do such prediction for every patient who is hospitalized, you can decide whether you need more resources down the road. So how do we define deterioration event? There is a classical early warning score, which is called NEWS2, and it was adjusted to the COVID disease. So these are the parameters that get into the disease, and each value of the parameter gives points, and it's simply a scoring point system. So each of these 8 parameters get its own score, and you simply sum it up and decide if the score is above 7 or above, it is considered a severe case, and this is what we want to predict. So tell in advance which of the patients are going to have a high COVID score, high MNEWS score in the next 30 hours. So the data that we had was patients from both Shiba and Ichilov, a little over 1,000 patients together, and the data originated from electronic medical records covering the parameters that you see here. And our approach was we have the data over time of each patient, and in order for this to be useful and not tell the doctor something that they already observe in the ward, we want to make the prediction at least 7 hours in advance. So if deterioration is at that point, we want to predict up to 7 hours ahead of the time within a window of 24 hours. So we are predicting 30 to 7 hours ahead of the deterioration event. So the time moves on. At this point, the prediction is within the window that we want to predict. So we want the early warning score at T3 to tell us that there is an event in the window, and this continues as the process goes on. So we make a prediction every hour for events that will happen within the next 30 hours, but at least 7 hours from the event itself. These are the data that we had. So we use the Shiba data to develop the model and to do the training and the testing, and we use the Ichilov data as an independent set from a different hospital. So here's a fuller picture. We take the Shiba data and separate it into a training and testing set. On the training set, we do 20-fold cross-validation in order to develop the model and the hyperparameters. Once we get the final model, it is trained over the whole training set and applied to the testing set. And finally, this is also tested on the data at Ichilov as an independent set. Okay, so there are many stages in preparing the data. I'll go over them very quickly. So we took adult patients that had scores, and we excluded patients who were severe, near, or very close to the admission. The way we looked at the data is to summarize the information we have every hour. So if there were multiple measurements, we average them in the hourly window, and we call these observations. And then we do additional exclusion of observations. So as I said, 6 hours prior to deterioration event, the data is excluded, and also 8 hours after deterioration events are excluded because we don't want to bias the result by predicting deterioration, which typically stays for a while until it is removed. In terms of the features that we used, we looked at 21 established risk factor score for severe COVID. And from each of these measurements, we created multiple features, looking at windows of 24, 72 hours and the full hospitalization period until the current time point. And we created features of difference between consecutive time points, the ratio, interactions, anomaly, etc., and excluded the features that had a high missing rate. Altogether, this ended up with about 500 features that were fed into the modeling. We needed to impute the data. Of course, EMR data is typically very sparse, so we imputed data for all variable and patient using a combination of two techniques, linear interpolation and multivariate imputation, which is a version of the mice algorithm, which is a popular imputation method. To select the feature, we tried two strategies. First was simple correlation with the target, and the second was to apply the XGBoost algorithm, machine learning algorithm, and use the feature importance. Eventually, we ended up using the second method because it was more effective. And the 100 top features were selected. You see here some of them. We applied a large number of machine learning classification models. You see them on the right. Eventually, cut boost, gradient boosting variant was the best. And you see here the results on the validation set of Shiba data. The ROC score is about 0.84, and the precision recall score is about 70.74. So pretty decent numbers. If we look at the most important features, the feature contribution was assessed using the SHAP values, and you see here that, as expected, age, temperature, startup deviation, saturation, maximum LDH, etc., are on the top of the list. Interestingly, the majority of the top features are not original measurement, but the kind of engineered features that we generated. as an evaluation, we applied the same model to the data from Ichilov, which was completely blinded until this point. And we see a slight decrease in the performance, but still a UROC of 0.76 and AUPR of 0.7. So this means that, of course, one can choose a point along the curve in order to balance precision, sensitivity, etc. Just to give you an example, if we wish to have a positive predictive value of 0.9, we have a sensitivity of nearly 50.5. So this means that if you are willing to have a 10% false positive, you will catch half of the deterioration cases. Okay, the work still goes on, and we have now a larger cohort, and we also want to try additional events. In addition to Ichilov and Shiva, where we have now longer data sets, we also have data from Asuta, and we have a collaboration with UCLA where we are going to use their data as an external validation set, altogether nearly 10,000 cases. And the idea is to do training over multiple centers together and to look at multiple waves a little more systematically. So one point that we are observing is looking at a single prediction based on the measurement at the baseline, at the entrance of the hospitalization, and predicting the deterioration anytime within the hospitalization. So this is the baseline prediction, and the longitudinal prediction is similar to what we have done before, but with possibly different outcomes. So here is an example of preliminary work of predicting mortality using baseline model. So this is using only the data available at the 24 hours after admission. And again, you see that the values are similar, AUROC of 0.86 and the AUPR of 0.63. You see here the results of the different models that we tried in terms of AUROC. Again, cut boost is winning. In terms of AUPR, a linear SVM happens to be the best model. So here we are predicting mortality, not deterioration. Another type of analysis that we are doing is evaluation across the different waves. So one caveat is that maybe the nature of the patients, the characteristics of the patients and their response changes across the waves. And the concern is that maybe what we developed will not be useful for the next wave. So we developed a variety of strategy of separating the training and the validation across different waves. You see here an example of two different ways. So K-fold is just separating by the training across waves. Sequential uses the past waves to learn and predict on the next one. And the next wave uses only data from the current wave in order to predict on the next one. And here you see again a baseline mortality model for sequential prediction across waves. On the left, you see the AUPR. And on the right, you see the AUROC. In blue is the first iteration that uses only the first wave data to train and test on the second. And in orange, you see the second iteration where we train on the first two waves and test on the third. So the good news is that having more data, even if it is across waves, is useful, and the prediction improves for the next wave. Another project that is led by Omer in my group is looking at trying to develop a novel imputation method. So we realized in the analysis that the current imputation methods are limited. So Omer developed a new iterative imputer that combines a weighted version of mice with forward filling. And this combination is specific to the patient, the variable, and the observation. And preliminary result that on the original problem that I've showed before is where we try to predict deterioration using the MNU score, get improved results. So you see that the AUPR improves and the AUROC stays the same. I should say that the exclusion criteria are different because now we are able to handle a bit more data. So therefore the data is not exactly the same. On the other hand, we didn't optimize the hyper parameters. So with that optimization, we expect the result to improve even further. So this work is still going. I think it's highly promising. Summing up, we developed a machine learning model for the early prediction of deterioration of corona inpatients. The early warning tries to predict at least 7 hours and up to 30 hours in advance those patients who will have MNU score above equal or above 7. This model or predictor can be applied repeatedly upon every hour of the hospitalization. And this can be done using both the baseline and the longitudinal data. We obtained a robust external validation on data from a separate hospital, from Ichilov. And we are continuing this work to additional analysis and substantially larger data set. Finally, let me thank my group for all the help and the funding sources. Thank you very much.
All right, we have time for some questions.
No, is that?
The machine learning model to remove, for example, age or sex, what's the performance?
If we remove what?
Age.
Age. Oh, so as you see, age is one of the top features, and not by chance, MNU's score adapted to COVID. The adaptation was adding the age as a factor. So I'm not sure if we did this specific test. Omer, did we do it?
We just validate that using age by itself, make the model was the final model that wants to then outperform any other model with other features. Age was the best framework.
Yeah, so definitely this is one simple feature that should not be missed by any way. Yeah.
I have a question, actually.
Sure.
Did you see different, did you try looking at different waves and independently and seeing if the predictors are different under different waves? The most significant.
So as you see, the preliminary analysis that I showed at the top, at the end shows that actually one can learn from one wave to the other. I would assume that the models will not be exactly the same, but on the other hand, if you use, I don't know, waves 1, 2, 3 to predict for wave 4, since you have additional data, more data, then
Yeah, that's
it will improve.
You
Yeah.
might learn about the dynamics of the disease from differences.
Yeah, I agree, but the good news that you can boost the model by using additional waves. You don't need to really start from scratch every new wave and learn everything. Yeah.
Great. So if you have no further questions, we'll thank Ron